that problem was, what's the second part of that problem? Adding aqueous sodium carbonate. Does it make it more soluble? And sodium carbonate is what? It is a source of carbonate ion, correct? And if I have this reaction and it has carbonate in it, adding carbonate to it is increasing its concentration. And if you increase the product, how does that affect my equilibrium? Shift to the opposite. So solubility is increased? No, it is decreased. Perfect. Last but not least, I have this one. Adding solids do not affect equilibrium. So in my reaction, I could have added solid coupled to carbonate. That is my reactant, correct? Does adding a reactant affect my equilibrium? In general, it does. Except this is a solid. And therefore solids do not affect equilibrium. So that's the big takeaway message. That's the big one, correct?
Adding a solid will never increase the solubility.
No, adding the solid to a solution does not increase its solubility.
So for our purposes, we need to knock that right off the
Yeah,
choices.
yeah, you know that one. That's not true. Yep. And with that, we finish chapter 15. Whew.
Okay, so, I'm sorry, so adding a solid to
An equilibrium, adding a solid reactant to an equilibrium does not affect its solubility or product, you know. To the,
this is solid.
any solid that appears in the equilibrium does not affect that equilibrium itself. It can be anything. Let's do this one. Ooh. So chapter 16, fair question. The question is, which one cannot behave as a bromelauric acid? The first thing you must do is define what a bromelauric acid actually is. What is a bromelauric acid? It's a proton donor. So you make sure you define that it's a proton donor. To be able to donate a proton, what must you have? A proton, a hydrogen atom that is acidic, correct? So if you don't have a hydrogen atom, can you be a proton donor? No. So for example, this guy here, this B1, this is sodium acetate. Of course, that means I have sodium ion. Sodium ions are put on the side. I don't care about this guy. The acetate. The acetate ion is the conjugate base of acetic acid. You see there is no acidic proton here. Can this behave as an acid? No, it is on the other fact a conjugate base. What about sodium ion? To be an acid, according to bromelauric, you must have what? Hydrogen. Sodium ion is nothing, right? So is it a bromelauric? No. So the answer is this one. It's not a bromelauric acid. Let's evaluate this one, hydrochloric acid. Is hydrochloric acid a bromelauric acid?
Yes.
Yes, it is. How do I know that? First of all, it's a strong acid. And this whole strong weak thing comes from bromelauric, right? And it has, of course, that huge proton right there, in case you missed it, and it can be donated. It's always an acid. And here I have this guy, sodium dihydrogen phosphate. The sodium does nothing, as we established earlier. But this dihydrogen phosphate, this guy here, is amphiprotic. It can do what? As an acid, it can give away one of these protons here to produce hydrogen phosphate ion. Do you see that? Do you see it? How do you know it's amphiprotic? Because A, it has a negative charge, so it's able to accept a proton, and B, it has two hydrogens here. I know it's triprotic, the phosphoric acid, H3PO4 is triprotic. Has three of them that can be lost. This one lost one, so it's able to gain one back to become phosphoric acid again. But since it still has the two there, it can lose any of these two, so it can behave as an acid as well. So this one's able to do both things. Yes?
A proton donor can also be anything other than hydrogen, or is it just a hydrogen?
No, a proton donor is a hydrogen atom with a positive. A proton donor has to have a hydrogen atom with a positive charge that can be given away.
Okay.
Right? That is key. Has to be a acidic proton. Anything else, guys? We're good? Yeah. Yeah, so when it ionizes, it has to be able to have a proton form. If it cannot do that, then it cannot behave as an acid, according to Brunson and Ori.
And also know a trick, you never take a hydrogen away from a carbon.
Oh, yeah, so the carbon,
That's an easy way to do
yeah,
it.
that's an easy way to distinguish acidic protons from non-acidic protons. Carbon-connected hydrogens are not acidic under most circumstances.
For our purpose.
For all purposes, in this course, they're not acidic. Okay? Let's continue. Question number 2. This is different. This is about Lewis. And Lewis is all about electrons. Electron either being donated or being accepted. We want a base. A base is an electron pair donor. So I define that first. First of all, ammonia,
Yeah.
you know it's a base from Chem 1. So is it going to be a Lewis base? Yes. Whatever was a base back in the day is still a base for Lewis purpose. Because Lewis is more general. It actually encompasses more stuff. Okay? And you can see that it has an electron pair there, so it can be an electron pair donor. What about this one, carbon monoxide? Ooh, I did a bunch of stuff to that Lewis structure, right? I drew it out, I put the lone pairs, and then I gave it its formal charges. Think that's important? You think that's important? Check it out. It has a negative charge. Huh. Anions, or things with negative charges, are able to donate these electrons? Yeah. Anions tend to be Lewis bases. Anions tend to be Lewis bases. What about cyanide? Oh, cyanide is an anion, therefore it is an electron pair donor. It's a Lewis base. But what about cations? You think a cation is going to donate more electrons? No, it just doesn't make sense, right? And therefore, cations are not electron pair donors, they are electron pair acceptors, they are acids. Questions or just stretching? Any questions, guys? Lewis acids and bases, electron pair donors, electron pair acceptors. Do you want this on your exam?
Yeah.
Yes.
Yes, this is good, right? You have a solution. You need to dilute this solution so that the pH is now 2.9. This is a chemistry 1 problem. This is a strong acid, correct? And I'm giving you its pH at that in this situation. I give you also the pH that I want. And I'm asking you what volume must this acid be diluted to get that pH. What do I know? I know if I have this initial pH, that pH gives me also the hydronium ion concentration, 10 to the negative pH, is that, right? And therefore, that is the concentration of my acid because this happens to be a strong acid. For all the strong acids, monochloride, hydronium ion concentration is the concentration as well, right? These two things are the same. Perfect. What do I want? I want this new pH. So I want the hydronium ion concentration to be 10 to negative that new pH, 2.9. So that means the concentration of my acid is going to be a new thing that is like diluted now, that one, correct? Yeah. Diluted, concentrated, that is dilution problems. Equation from Chem 1, C1V1 equals to C2V2. Do you recall this equation? You do now. That's a good answer. So perfect. So what do? Concentration 1, given. Volume 1, given. Concentration 2, of course I have it. Concentration 3, volume 3, I'm sorry, I don't know it. It's X. What do? I solve for X. I'm telling you, this class should be called Algebra 2.0, right? Question?
How come you can't just look at it and say, okay, I'm gonna almost double my pH, therefore I'm almost gonna double the milliliters?
Absolutely. You cannot do that because you cannot do Yeah, you can see it.
Well, if you double the pH, then you just double the,
No. If you double the pH, that is almost 10 times bigger. Remember, every change in one in pH is 10 times larger change. So you go
like
from
20
13.
times, then 20.
Yeah, in this case it's 20. It's 200 times. 20? No, 20 times bigger, because this is more than double.
So for every 1 point, it's 10 times.
For every 1 point is 10 times, but this is 1.5.
Right, so it's almost double. So
It's
you
almost double, yeah.
can look at it.
Almost double 20. It's harder to do it because it's not easy. Sorry. It's harder to do it in your head. This one is easier to do C1, B1 equals C2, B2. I know in class I did 10 ratio, and that was for buffers. That's easier to do. Any questions about this? Yes?
So how do you know C1 is 10?
What?
That C1 is 10.
C1 is concentration 1. V1 is volume 1. Concentration 1 is that. Volume 1 is that.
How do you know the concentration?
The concentration of my acid is given from the hydronium ion. These two things are the same because this is a strong acid. For strong acids, the concentration of hydronium ion is equal to themselves, so long as they're monoproduct. Okay? That you need to know. So let's say I have 10 molar hydrochloric acid. That means my hydronium ion concentration is 10 molar as well. Let's say I have half a mole or half a molar nitric acid. Then my hydronium concentration is also half molar, right? So you need to connect those. That's an important connection. Okay?
You would ask for the pH in this question.
Yeah. And now in this type of question, I asked you the final volume. Is that the only way I could have phrased this?
No.
What else can I ask?
How much water you have to add?
How much water you have to add, and then you subtract your initial amount from the final amount, and that gives you volume added. Anyone else? That was in the homework. That was in the homework. Let's do this one. I love these table things. I have a table with a bunch of bases. I'm asking you for what?
What the weakest base.
I want the strongest conjugate acid. I didn't give you any acid. What did I give you? Bases. I gave you all KBs. I know that KB represents the strength of my acid. The greater the KB, the stronger my base. Right? Sorry. Base of my base. Right? B for base. Right? The stronger the base, bigger the KB. Got it. You need to know that. We also know one more thing. For the conjugate pair, if Ka goes up, Kb goes down. So what do I want? I want the strongest conjugate acid, correct? So I don't want the weakest. So if I have the,
Weakest base.
I want the weakest base, correct? I evaluate my table and figure out what I have. My largest Kb value is that one. That corresponds to my strongest base, correct? Which is this one, and therefore its weakest conjugate acid will come from that one, correct? But I don't want that. What do I want? I want the opposite. So I select the smallest Kb value, which is that one. That is therefore my weakest base, which is this one, which produces the strongest conjugate acid. As Ka goes down, Kb goes down. Question? Yes?
If you had given us PKB,
And
you
that
wanted
is the
the
next
strongest
question.
then it would be diethylamine, right?
Yeah, that's the next question. Anyone else before I continue? Is that okay? Because the next question is not with Kas, but with Kbs. Look at that. And not just Kbs, but pKbs. And what is the relationship here? The strength of the base increases Kb, but what does that mean for pKb? It is the opposite, it goes down, correct? So what do I want? I want the strongest base. Which is the strongest base? The strength of the base increases pKb, which means the pKb is going to be the smallest. So I want the lowest pKb value. In this case, it's this guy, which is my strong. The strength of an acid increases with Ka. The weakest acid is the one with the lowest pKa. The relationship is still the same. Now, if we're looking about the conjugate pair, so if you're asking me which of these conjugate acid, okay, I will look for the strongest base, which has the lowest
Right.
pK. It's still the same thing. Because this is the strongest base, it produces the weakest conjugate acid. Yeah.
If it's at the strongest conjugate acid, then you would do isoquanone.
Correct. So I could have asked the strongest acid, which is from the weakest base, which is the one with the largest Kb value, which is this guy.
Is PKB the same thing as POH?
No. You use PKBs to find POH using a modified version of the Henderson-Hasselbalch equation. We don't use it, and don't use it because you'll get confused. We only use pH is equal to pKa plus log of base over acid. That's all you need to use. Do not try to do POH with that equation because you're gonna get the acids and bases mixed up.
Can you say that one? pKa equals OH.
What?
The formula you said pKa.
Oh no, pH is equal to pKa plus the log of base over acid. It's provided in your equation. You don't have to memorize it. Yeah, you don't have to memorize it.
I know to get from Ka to pKa or vice versa.
Yeah, so how do you do that? How do you go from Ka to pKa? Ka and pKa are related by this little p, and this little p stands for negative log. So whatever it is, just take the negative log of that, and that gives you pKa.
But conceptually, what does that mean?
It is just a way of changing this number from one value to a logarithmic scale. That's all that means. Yeah, and we use it for convenience because as you can see, these numbers are nice and easy. It's like 1.2, 3.8, 5. We love numbers between 1 and 14, right? Because if you look at the other table, look at those values. Yeah, exactly. We don't like those too much. Let's do this one. Yes.
So acids go with conjugate bases, right? Bases have conjugate acid.
Correct. So whenever you have an acid, it will have a conjugate base. Whenever you have a base, you have a conjugate acid. And the relationship between the equilibrium constants is if one goes up, the other one goes down. Because they're all related by this expression. Ka times Kb equals to Kw, which is right there. See that? For a conjugate pair, Ka times Kb equals to Kw. So if one goes up, the other one has to go down. Right? So let's do this. What is the conjugate acid of this species? And that is the answer. How do I know this is the conjugate acid of this one? Because A, a conjugate pair differ by one proton. If I don't want a conjugate acid, that means this species is behaving as what? A base. So if you take this one as a base is what? A conjugate proton or a proton acceptor or a proton donor? Acceptor. So it takes a proton, bloop, and it becomes conjugate acid. Which you see there. Right? What do you think of that?
Probably won't have a question.
You will probably have a question like this. Why not?
No, I'm saying that'll be combined.
With something else.
Yeah, it's not just gonna be, what is the conjugate acid?
Which is the conjugate, which is a conjugate pair? It's a great question. I'll give you a bunch of pairs. And then you have to analyze all of them.
Well, when you ask that, you say like which one is like the acid which is the conjugate base?
Or which ones are not the same. Example, I give you this one. Let's do this. You have
You'll combine 6 and 7 in one question.
HBO4, correct? That's one thing. And then I have these. Are these conjugate pairs?
That's the chart.
Where's the chart?
No, this is a compound. No, they're not. This is not the conjugate pair of this. What is the conjugate pair of this? It's this.
Base is PO43.
Yeah, sorry, yeah. No, but let's say you have this.
The conjugate base is
Minus
that.
2. Let's say that. Okay.
PO43 minus. Conjugate base.
Is this a conjugate pair?
No.
No. And then the conjugate pair of this one would be something like this, right? These are conjugate pairs. They differ exactly by one.
That's the conjugate, bottom of the conjugate acid at the top.
Correct. It has an extra proton, no proton, one charge difference.
The conjugate-
Remember, they have to differ by one charge, and they have to differ by one hydrogen atom in there. But check it out. The one that has the extra charge has to decrease in charge, right? So the charge becomes less positive when you lose a proton. I give you a really bad example of this. Ooh. That's one thing. And what about this?
Well, it would have to be CO2 minus.
No, yeah, it has to be CO2 minus.
They're not.
But these are not. This is carbon dioxide. This is carbonous acid. These things actually exist. They suck because they make this type of problem much more difficult.
So the conjugate base of HPO42 minus is PO43 minus.
Correct. So if I have this guy, I have this as its conjugate base. This is the acid, this is the base. I can do one more, H3PO4.
Conjugate acid.
This is a conjugate pair right here, right? This is a conjugate pair, and I can do one more. PO4, 3 minus. This is a conjugate pair. These are pairs, and these are pairs. But is this a pair of this one? No, because they differ by more than one proton. Remember, the definition is only one proton. Good. Let's continue with the next one. I have this CO2 one right there. See? I have HCO2 minus. What is its conjugate base? It's CO2 minus. You see, I have this guy behaving as an acid so that it can produce a base. The acid is a proton donor, correct? So it has to get rid of one proton, so it produces CO2 minus, which is the conjugate base right there. So you have done it. Any questions about this?
When you remove the hydrogen, don't you increase the charge?
Absolutely.
It should be
So-
CO2 minus
That's
the
all,
conjugate
yeah,
base.
because you see.
Which one?
Number 7, CO2 minus the conjugate
No,
base.
this doesn't have a charge.
It does in the question.
Oh, shoot, I forgot. Yeah, good call.
Oh, you're not going to dinner tonight.
No, man, that's a
You're gonna have a hungry man TV dinner, maybe.
Yeah. 2 minus, there you go. Right?
So,
So the answer is CO2 too.
Correct. Because they have to differ by a charge of, by one charge, right? Good call. See, I put it correct there and then I messed it up, right? This is 2 minus, right? Oh. And last but not least, I give you the Ka and I ask you for what? No, I give you Kb and I ask you for Ka. And you need to know the relationship between the two. Is this one? Is that equation provided? No. This you need to know. How likely are you to use that in that exam? 100%. How much are you going to use it? Like 10 times of this. Yeah. Yeah, a lot. So you're definitely going to use this. You know Kw value. Is that provided? No. So you need to know it. And then you get your value. You get your answer. Plug in and play. Who loves plug in and play problems? Yes.
Can you please explain KW?
Kw is the ionization constant of water. This is all occurring in water. These are ionizations in aqueous solutions. So Kas and Kb's are always related to Kas and Kb's are always related to each other by Kw. You need to know Kw value for water, and then just use it to solve for Kb if you know Ka, or Ka if you know Kb. Yeah. So you generally use a form of this equation. Kw divided by Kb gives you Ka, or Kw divided by Ka gives you Kb. It's one or the other. Yep. What are we doing here? Ooh, this is a tough problem. Ah, man. What do we have? We have a solution of sodium carbonate asking you for the hydroxide ion concentration, and I give you carbonic acid with 2 ionization constants. That sounds like hell, all right? And I tell you why. Because Ka here represents the reaction of carbonic acid to produce bicarbonate ion. Ka2 shown here represents taking this ion minus. Keep on missing the signs, guys. To produce this carbonate ion, correct? What is the reaction you actually have in solution? You have sodium carbonate. That is a source not of anything else here, but of carbonate, the last product here. So what do you do then? Do we use K1 or K2 then, if you have these?
K2.
You use Ka2, but this is not, you don't have the acid. What do you have? Conjugate base. So you take that and figure out Kb based on this guy. So take your Kw, which you're not, you know, 1.14, divided by your Ka2, which is given, and that gives you Kb for carbonate. This is Kb of that particular compound. With that, you can solve. You know, you must know this by now. This expression, Kb equals to x squared divided by the base concentration. And if this was an acid, what would it be? Ka equals to x squared divided by the acid concentration. So it's the same thing. So if this is a B, this is a base. If it's an A, this is an acid. And if you're monoprotic or if you have a single hydroxide, you always solve to this. Okay? You might as well just memorize both versions because you use this a lot. Okay? And you solve for x. If you have Kb, so you plug that in. You have the base concentration, it's that. That number, 0.22 times 2.08 times 10 to the negative 4, gives you a number, a square root of that, because that is x squared, gives you the hydroxide concentration.
So you don't want to use that equation, Kb over.
Whenever you only have a weak base in solution. So if you only have weak base, then Kb equals to x squared over base. What is the opposite situation? What if you only have acid? Weak acid, of course. Then Ka equals to x squared over your acid concentration. And x here is equal to hydronium. And here x is equal to hydroxide. How easy is this problem now? Not too bad. Let's do the next one. Oh, look at that. We have a solution with only an acid. Look at that. You have its hydronium ion concentration, so you know what HA is, right? I know the initial concentration. It is 0.1. So I have this. I have hydronium, and I have the acid concentration. So what do I do to solve for Ka? Plug it in. What do you think? Who likes this type of problem now?
Wait, so what was the difference between the other one, the previous question?
The other one had base.
I know it was base, but.
So it is the same thing, but because this is a base and this is a base, then X is hydroxide. Here you have an acid, X is hydronium. That is the difference. What does a base produce? What does an acid produce? That's the difference. Any questions? What do you think? Last but not least, I got one last problem. It's huge. It has two Kas. Right? But because I have the actual acid of this polyprotic acid, I remember from lecture that if you only have the fully protonated acid, you use the first Ka only, because the second one is, how does the first ionization compare to the second one? The first one is much larger, so it produces most of the hydronium atoms. So you don't worry about Ka2. So you don't use Ka1. So we do a little ice table, initial amount, 0, 0, minus x plus x plus x, these two amounts. Ta-da, that's it.
But wait, Helen, so
But wait, hold on, what?
why do we use, like, why do we have to choose again?
Because this one has two protons there. You see that?
Yes.
This is, the first ionization is for this reaction. In the second ionization that is given here, you take this guy and it uses a proton as well. But the second one is too small to matter.
It's not on the test, quite, right?
Oh yeah, this is not an exam. Yeah. I put a note on it. It's too small, so you just put on it, but this is not an exam. Yeah. Good call. I put a note. Hold on. After that. Have you seen that?
Blur.
No. There you go. the hydronium ion is a lot larger, so it's like 21, then at equilibrium that it becomes the same thing because X is small, so that's your answer. So the question was, what is the concentration of my acid at equilibrium? And the answer, if the concentration was very large, then the equilibrium would not affect it. And the answer would be exactly the same thing. You can actually save yourself the time. I've seen this type of problems in exams. Like where you are given a big problem like this. You see how big this problem looks like? And it has a lot of information there. And you are like, oh, I have to do a calculation, right? But if something, very small changes. If I make this 0.21 by 21, see, I just changed one number. I don't have to do any of this. I just see that this Ka is small compared to 100 times the concentration of.
The bottom, actually.
Yeah, so let me show the bottom. So if I make the concentration 21, then 100 times that Ka is still less than this. And therefore the concentration of my acid is going to be essentially the same thing. Yes?
Do you think in the exam that we should always do the times 100 or?
Times 100. It's always a good check. You should still do it. The reality is, okay, let's be honest here. The reality is you have no quadratic problems in your exam. So for all intents and purposes, K given are always going to be very small compared to initial amount. Yeah. That's it. That's the last problem. And with that we finish. And it's right on time.
So 12 and 13.
Out of your test.
Oh, 12, that's it. Did I miss something?
No, don't cover now, that's it.
What happened? Did I miss it?
Can't do a test now. Number 12 is definitely in the test.
Oh, it's here. Is this it? Yeah, oh, sorry. I moved it. Yeah. I forgot. Oh, I thought I had perfect timing. See? What is the effects of salt? You need to know the effects of salt? Yes. If you are running out of time or if you cannot see it, you can memorize the table that is in your textbook. Some people prefer memorization. The cations that are formed from strong bases have no effect on pH. So potassium, lithium, and potassium hydroxide, lithium hydroxide, no effect on pH because they come from strong bases, right? Ammonium, on the other hand, is a conjugate acid of what? NH3. A conjugate acid of a weak base is going to have an effect on pH. This will make the solution acidic, correct? We evaluate the cation, the anion there, chloride. Chloride comes from what? Hydrochloric acid. Hydrochloric acid is strong, chloride, no effect, because it comes from a strong acid. So therefore, I have something that's acidic, the other one has no effect, the solution is acidic. On the other one, I have lithium, no effect. But what about the cation? The anion, sorry, is nitrite. That is a weak base from a weak acid, correct? So this ion comes from a weak acid, therefore it has effect on pH. It's a basic ion because it's a conjugate base of a weak acid. It's a conjugate base of a weak acid, therefore the solution will be basic. And then I have acetate.